All right, good morning, everybody. It's a little after 9, so I think we'll get started. Thanks for coming out this morning. So in this, the 16th meeting of SLLOBS, we're going to do sort of a gentle introduction to regression and linear modeling using R. So this is a topic that probably many of you are familiar with. You probably fit linear models in R, Excel, Stata, some language, some program. But today, I really want to sort of dig into the weeds a little bit, talk about a couple of metrics that we use to understand the relationships between variables, and also dig into how we fit basic linear models in R, and probably the bulk of the lecture will be about how we actually interpret the outputs of those models, and specifically the p-values associated with parameters in the models that we fit. And I probably don't need to motivate this too much, but I always have one of these slides in the beginning. I think in biology and biomedical science generally, we're very frequently interested in the relationships between two or more variables. So one really famous early example of regression is from Francis Galton's work, understanding the relationship between the heights of parents and the eventual heights of their offspring. So I've just replotted some data here from an 1885 publication where he's looking at, on the x-axis, the sex-adjusted average height of both parents, so-called mid-parent height, and on the y-axis, the sex-adjusted heights of their children in inches. And you can see this pretty clear positive trend indicating that generally taller parents tend to have taller children. And if we have these relationships between variables and we want to better understand them and quantify them and ultimately use them to predict data that's incoming in the future, we like to fit models. Oftentimes it's simple linear regression models like the one that I've drawn here. So in the SLLOBS talk today, we're going to just go through some basic concepts. The first are two different metrics that we often use to quantify and measure the relationships between variables, called covariance and correlation, two things that you've probably heard of before. Next, we're going to talk about how you actually go about practically fitting linear models in R, which is pretty straightforward. And then lastly, which is going to be really the bulk of the lecture, is going to be how to interpret the model outputs, and specifically the p-values that are returned after you fit a linear model in R and are actually interested in gauging how well it worked in practice. But to start off, let's talk a little bit about these two metrics, covariance and correlation. So the first one, covariance, is one that maybe you've heard before. And pretty simply, covariance measures, quote unquote, the joint variability of two random variables. Put another way, basically all this is asking is, do large values of some variable tend to correspond with large values of a second variable, and vice versa? Really all it's asking is, do two variables covary? And mathematically, covariance between two random variables, let's call them x and y, is defined like this. And so for those that are maybe more familiar with the mathematical syntax, you might appreciate this right off the bat. For those that aren't, it's actually fairly straightforward. We're going to walk through how you actually calculate covariance by hand in R using some toy x and y data points. But if you're not super familiar with the mathematical syntax, really the only thing to keep in mind here is this big E of x or big E of y syntax. So the big E symbol basically just stands for the expected value. So when we're dealing with random variables, the expected value of a random variable for our purposes today is basically just going to be the mean of that variable. Mathematicians might quibble a little bit with that definition, but big E of x is just the mean of x for our purposes today. So this is how you calculate covariance. But I figured it would be useful to actually go through this in R and calculate covariance by hand for some toy variables, x and y, that we'll define. Okay, so let's actually calculate covariance. So the way we're going to do this is we're going to define some random x and y data points. And the way we're going to do this is going to be very straightforward and very contrived. So to define our x values, we're going to take a sequence of integers from 1 to 10. And for each of those integers, we're going to take a random draw from a normal distribution that's centered on that integer. So we hit number 1, we're going to take a random draw from a normal distribution centered at 1. We hit number 7, we're going to take a random draw from a normal distribution centered at 7. We're going to do the exact same thing for y. And you'll notice here at the top of the script, we've got this set.seed123 line that I've added in there. So without getting into the details too much, set.seed is a function you can use in R to set the so-called seed number for the pseudo-random number generator in R. Now what this is going to do, if you run this before you run anything else, the random draws or the pseudo-random draws you take from the normal distribution on your machine are going to match exactly the pseudo-random draws on mine So all of the values that we calculate from here on out throughout the slides will be the same on my machine and the same on your machine, as long as you run that set.seed 1, 2, 3. So you'll first obviously realize that we're defining x and y in the exact same way here. Basically, we're just introducing some noise into the x and y variables here. But I think off the bat, you can expect that they're going to be somewhat, they're probably going to covary since we're defining them in exactly the same way. Okay, but the first step of calculating covariance is to calculate the so-called residuals of x and y. And the residuals, as you can see up here in the math equation, we derive by taking every value of x and subtracting the expected value of x, which in this case is just the mean value of x. We do the same thing for y. And so in R, what this amounts to is you calculate your x residuals by just taking that array of x values and subtracting for each value the mean of x. And we do the exact same thing for our y values. Okay, so just we can quickly go and see what this looks like in our studio. Should probably here copy and paste. And you can do the same on your machine. And you can see what these look like. And so if we look at both the x and the y residuals, and you can look at this on your machine, what you can probably already tell is that on average, what we're seeing is that smaller than average values of x tend to correspond with smaller than average values of y. That's what a negative residual ultimately means, is since for each value of x we're subtracting the mean value, a value of -5 here means that this value of x is basically 5 units smaller than the average, and this value of x way at the end is about 4 units larger than the average. And so on the whole, you can see that the residuals of these two variables seem to covary with each other. And this is essentially what we're going to be testing when we calculate covariance. Okay. So the next thing that we're going to do when we calculate covariance, once we have the residuals of x and y, is we're just going to multiply them together. We're going to take the product of the residuals. And that's also pretty straightforward. And if we think about what we're actually assessing when we calculate the product of the residuals, this kind of goes back to what we were just talking about. Basically, if smaller than average values of x tend to correspond with smaller than average values of y, those residuals are both going to be negative. And so when we calculate the product of the residuals, they're all going to evaluate as positive. Smaller than average values of x are negative, smaller than average values of y are negative. Similarly, larger than average values of x are positive, and same goes for y. So if this trend holds for every single pair of xy values, every product of the residuals is going to be positive. And that's going to indicate that there's covariance here. Now the last step that we're going to do, which is this last big E, is we're going to take the sum, or we're going to take the unbiased mean of the products of the residuals. Now, normally when you take the mean of values, right, you take the sum of values and divide by the number of values. It's pretty straightforward. Now, the unbiased mean is this sort of related concept. Without getting into the weeds too much, when you take the unbiased mean of a series of values, you don't take the sum and divide by the number of values. You actually take the sum and divide by the number of values minus 1. Now, this is what R does when it calculates covariance, which is why we're going to do it in our manual calculation. And we don't really need to get into why this is necessary, or some would argue unnecessary for this few values. But you take the unbiased mean of your product of your residuals, and that is the last step in calculating covariance. So if you do this on your machine, and then you actually evaluate what the covariance is that you calculated, you can see that the covariance between x and y, in this case, is 7.808, etc. Now, as you might expect, there's an automatic function to do this in R. You don't have to do this by hand if you want to calculate covariance. That function is just COV in R, which is a lot easier than what we've done. But if you run that, you should find, assuming the set.seed command was set, that the covariance calculated by R is identical to the one that we calculated by hand. So what does this actually mean? How can we interpret a covariance of 7.81 between our x and our y variables? Well, basically the only thing that we can take from the covariance is that a positive value of covariance indicates that the two variables we're looking at behave similarly. Large values of one correspond to large values of the other, and vice versa. Negative values indicate that they exhibit sort of opposite behavior. large values of one correspond with small values of the other. But that's really about it. And this is one of sort of the issues with covariance. It's a very simple metric, and it allows us to really quickly tell whether there is covariance between two variables. But the magnitude of the covariance, the actual value that's returned, is not really all that informative. And this is primarily because covariance is sort of an unadjusted or unnormalized metric, meaning that it's very, very sensitive to, and it's entirely dependent on the magnitude of the x and the y variables that we send into it. And we can test this, we can show this empirically, actually in a pretty straightforward fashion, using the code that I've written here, where in this example, all we're doing is we're taking our x and our y values and we're scaling them both up by a factor of 2. Now, intuitively, scaling both of our x and y values by the same constant should not change the relationship between those two variables. They should sort of exhibit the same correlation, which is what we're going to test next. But you can see that even though they're scaled by the same value here, if you actually calculate a new covariance value for these new x and y values, that number is dramatically different than the 7.81 number that we calculated before. And this is just because the x and y values have changed. The magnitude of those values have changed, and so the covariance changes. It's still positive because the relationship is the same, but it's hard to interpret what that covariance value actually means, other than its sign, essentially. Okay. So covariance is this unadjusted metric. It's not normalized, but it can be useful. And whether it's positive or negative is still informative. But there's sort of a potentially better metric that we can use, which is probably one that you're more familiar with, which is the Pearson's correlation coefficient. So the Pearson's correlation coefficient, mathematically, is actually just defined as the covariance of x and y divided by the product of the two standard deviations of those variables, the standard deviation of x and the standard deviation of y. And in this way, the Pearson's correlation coefficient is kind of a nice, normalized, adjusted version of covariance, where now we're taking into account the magnitudes of the variables and the spreads of the variables that we're inputting into our calculation. And so again, since we've already calculated covariance, we can pretty easily manually calculate the Pearson's correlation coefficient on our toy x and y data. To do that, we just take the covariance that we've defined and divide it by the product of the two standard deviations of x and y. We get out the Pearson's correlation coefficient of 0.949, and we can compare that to, again, an automatic function that R has for calculating this, which is just COR for correlation. And we find that, again, our manual calculation is exactly the same as the one that's returned by R automatically, which is kind of a nice sanity check. Now, the Pearson's correlation coefficient takes on a different range of values than the covariance. As you may know, this correlation coefficient can take on a value from -1 to 1, -1, meaning that your two variables are perfectly negatively correlated, and a +1 indicating that they are perfectly positively correlated. So just to kind of sum up here, basically the difference between Pearson's correlation coefficient and covariance. Covariance, all you're really asking is, do two variables covary? Yes or no. Correlation, you're basically asking, to what degree do they covary? So they're useful in different ways, but oftentimes we tend to use correlation as the default metric, even though it's really just a somewhat adjusted version of covariance. Okay. So these are two nice metrics. These are two pretty simple metrics that we can calculate really easily, either by hand or using R. But arguably, if we're interested in the relationship between two variables, there's probably more we want to know. We probably want to better understand and model that relationship. And in particular, when we're looking at things like, say, the relationship between parents' height and children's height, in the future, we probably also want to be able to predict new values of y given new data points of x. We might want to predict two parents come into the hospital and for some reason want to know how tall their kid's going to be. We can potentially predict with some accuracy how tall their child is going to be, assuming we fit a linear model now to our data and move past simple covariance and correlation. So now we're actually going to jump into how we fit linear models in R, which is relatively straightforward. But there's sort of an important note that we have to make before we do that, which is that basic linear regression, or ordinary least squares regression, as we're going to be talking about today, in R, or just in general, requires that the data we're modeling are continuous, meaning that the data we're trying to model can take on any value within some range. So within the range 0 to 10, our values could be 9.562, they could be 1, they could be 0.3, etc. Now, we definitely can, using R, model different types of data, like count data, binary data, yes or no data, and discrete data. But for those types of data, those different flavors, we're going to have to turn to different forms of linear models, not just simple, ordinary least squares. Now, those somewhat aptly are named generalized linear models. And I think in a future lecture, we'll probably get to those types of models and how you model these types of data. But for today, we're going to deal exclusively with ordinary least squares, basic linear regression. And for that, we need continuous data. And the data set that we're going to be using today comes from a source that we've actually already seen. If you maybe remember, I think like 10 lectures ago, we talked about ggplot, and we used this mtcars data set that's included in R. This is a nice data set. It's built in with R, and it contains a bunch of different measurements of automotive metrics from a bunch of different makes and models of cars from, I think it's the late 70s or early 80s or something like that. And what's nice about the mtcars data set for our purposes today is that it contains both continuous and discrete and even other forms of data. So for example, it contains continuous variables like the weight of cars, which could feasibly take on any value within a reasonable range. It also contains discrete variables like the number of cylinders in a car, which obviously is going to be some discrete value of 4, 6, or 8. You can't have 7.62 cylinders in a car. Okay, and the question that we're going to be trying to ask today is a relatively simple one that's probably pretty intuitive, which is, can we predict a car's fuel economy or fuel efficiency using our knowledge of its weight? And you're probably guessing, well, yeah, of course we can. That makes intuitive sense, but we're actually going to test this empirically. Okay, so to load the mtcars dataset, it's really easy. You might have done it already. You just type in data mtcars, and then you can head that dataset to see what it looks like. And so we can do that really quick. We can just take a look at what this dataset looks like. And you can see that in this dataset, in your console, you've got makes and models of cars. And then for each make and model, you've got a mix of both continuous and discrete measurements. Continuous measurements like miles per gallon, and discrete measurements like the number of cylinders in a car. And this is the data set that we're going to focus on, and we're going to focus on the continuous variables in this data set. Okay, so we're trying to predict a car's fuel efficiency by looking at its weight. Now, we could just dive right in and fit a linear model, extract some p-values and coefficients, and figure out whether this is true or not. But I think one important thing to do whenever you're doing data analysis before you go in and fit linear models or any type of model is visualize the data. This is what I sort of evangelized about in the ggplot lecture, so I think we should do this now. And get a sense of whether this is even really worth fitting a linear model to in the first place. Because if it doesn't look interesting by eye, we can still fit a model, but it's going to be informative to look at it visually in the first place. So we can do this. We can load our ggplot2 library. I like to load that cowplot library to make the plot look a little bit nicer. And then we can just run ggplot on our mtcars dataset. And on the x-axis, we'll plot weight, which is our independent variable. And on the y, we'll add miles per gallon. And we'll use geom_point to actually plot the points here. Okay, and you can get the plot on your own computer. You can look at it up here. And what seems pretty obvious is that indeed there's going to be an apparent correlation between the weight of a car, which here I think is given in thousands of pounds or thousands of kilograms, I'm not sure. And on the y-axis is miles per gallon. And it seems pretty obvious here that indeed, as cars get heavier, their fuel economy is decreased. So this is good. This gives us an idea that we're in a good spot to be fitting a linear model. This is an appropriate place to be fitting a linear model. So as you might remember from the ggplot lecture, we can also just add regression lines to plots directly using this geom_smooth command. Here we're using geom_smooth with the linear model method. And we can add this directly to our data, or directly to our plot, and see what that looks like. And now we fit this kind of nice regression line to our data, and we can see that it's recapitulating that apparent negative trend between weight and fuel economy. But what's actually happening when we fit a regression line like that? What's actually being done behind the scenes to produce that nice regression line that R can generate automatically and really, really quickly? And this is really what we're going to be trying to figure out today. Now, ultimately, when you fit geom smooth method equals LM to a series of data points in R, you're invoking what's called ordinary least squares, or OLS regression. This is really the simplest and most basic form of linear regression that there is, but it's quite powerful. And in ordinary least squares, what we're trying to do is fit a line to our observed data such that that line deviates as little as possible from the observed data points. And we measure this deviation using residuals, which we've actually already calculated a little bit when we were looking at covariance. But essentially, we can denote each of the real dependent variable measurements, or y values, that we've got in the data set as little y. We can denote each of the predictions that we've made using our line of best fit as y hat. So each value of y will have a corresponding prediction y hat. And to get an estimate of how well our line is fitting, or how well our predictions match our real data, for every single value of y, we'll take the prediction that we've made, which is y hat sub I, we'll subtract the real data to get a sense of how close our prediction is, and we'll square it to account for the fact that sometimes our prediction is actually going to be less than the observed value. We're going to get negative values in here some places. So we square it to get rid of the negatives, and we do this, we take the sum of these squared differences for every single data point in our data set. And this sum of squares is essentially our measurement of how good our predictions match our real data. And ultimately, what we're trying to do when we fit ordinary least squares is minimize this sum of squares, this residual sum of squares. And that'll give us the best fitting possible line. Visually, this can look something like this, where we've got the same data that we just plotted, weight on the x-axis, miles per gallon on the x. Our real data points are shown in red. We've got our predicted line of best fit that we fit with geom smooth. And these segments indicate the residuals, the differences between our predictions and the real data. And so again, visually, all we're really trying to do in ordinary least squares is draw a line that goes through these data points somehow that minimizes the lengths of these segments, that minimizes the residuals that we've drawn. And this is essentially why it's called ordinary least squares. We're trying to minimize, get the least sum of squares. Yeah?
You said you square it because you want to get rid of the effect of negative values. But, I would add that by squaring it, you're also kind of penalizing the points that are furthest away from the line.
Yeah. That's a.
Maybe you're going to get to that anyway.
I was not. So that's a really good point. Yeah. So yeah. Yeah. And you can imagine, right, that this value is going to have a very small residual. Squaring it's not going to do all that much. But yeah, as was just pointed out, larger residuals are going to get penalized more. And that's actually, that's a pretty important aspect of the ordinary least squares method. Yeah. So this is essentially the method visually, and as we just showed mathematically, and it's relatively straightforward. And if we want to fit it in R, it's also pretty straightforward. The way we do this is simply defining, this is just our ordinary least squares model. And to define it, we just type LM for linear model. We give our dependent variable, our y value, the miles per gallon, this little tilde symbol, and our x values. The little tilde symbol in R is sort of the default symbol for indicating as a function of. So with this syntax, we're saying, let's try and predict fuel economy as a function of car weight. And this tilde symbol is how we do it. We then also ask, or we tell R the data set that we're trying to use so it knows how to interpret the MPG and WT symbols that we're doing there. Okay, so let's fit our OLS mod, predicting miles per gallon as a function of weight using empty cars. Okay, that's it. We just fit a linear model. Easy. Okay, one quick, maybe not so hot take, but something that I like to mention is that linear regression, even if in its most simple form, I would argue is still machine learning. So what you just did when you fit your ordinary least square model, you're now a machine learning expert, because by fitting a linear model, you have trained a model on existing data, your x and y values, and you in the future can use that model to predict new values of y, your response variable. So everyone in this room is now an expert in machine learning because you fit an ordinary least squares model. Congratulations to everyone, and I stand by this forever, that regression is actually machine learning. Okay, so now that we've done that, we can actually go forward and spend a little bit more time, I think, talking about how to interpret model outputs and specifically p-values that come out of fitting a linear model in R. So there's a really powerful function in R once you fit a model, which is just called summary. We've actually used this before to investigate and get summary statistics from data frames. But if you run just summary on your ordinary least squares model, you get out this fairly verbose model summary. And this tells you all sorts of information about how well your model fit and gives you many more details about the vagaries of your least squares model. So let's actually spend some time and walk through each piece of this model output and how to interpret it. So first, it's just reiterating the exact model you specified. So if you get lost, if you're fitting tons of models, you can always come back and reference that. We also get this summary of the residuals calculated by the model. And this is, I think, fairly self-explanatory. The one thing you can keep in mind is that the mean of your residuals should always be 0. And so we would expect the median of the residuals to be pretty close to 0. And indeed, that's what we find. But really the bulk of what we're interested in and what most people's eyes jump straight to is this portion of the model output, which is the coefficient table, which gives you the values of the coefficients for the parameters in your model, your intercept, and perhaps most importantly, the p-values associated with those parameters, giving you a sense of basically how good your model is at predicting the thing you want to predict. And then lastly, you get a little bit more detail about the model specifics, and we'll talk a little bit about that later, assuming we have some time. Okay, but I think it's important right now to focus a little bit more on the coefficients in the model and the significance tests that are being done. So specifically, the first thing that we can see in our model output is that the point estimate of the slope is negative 5.3445. Now what this means is that for each unit increase in weight, in this case a unit increase is like 1,000 pounds or 1,000 kilograms or whatever that measurement is made in, we're seeing a decrease of about 5.3 units of miles per gallon. So in plain English, every 1,000 pounds a car gets heavier, it loses about 5 miles per gallon of fuel economy. And the slope of a model is often denoted with this beta symbol, and I'll be using that for most of the rest of the talk, just to keep things simple. But whenever you see beta, that just basically corresponds to slope in a simple model like this with just one predictor. We also see that the standard error of the slope estimate is 0.559. And essentially, the standard error of your slope estimate is, in a sense, a measurement of the uncertainty of that slope estimate. You can imagine that, as we've talked about, or Aaron talked about with t-tests, if you were to take 1,000 samples of 32 XY points of wild type weight and miles per gallon measurements, took 1,000 samples from the same population, and calculated the standard deviation, that would be equivalent to basically the standard error of your slope measurement here. But without getting into details, basically the standard error here just represents your uncertainty surrounding your point estimate of the slope. Okay. Now, as Aaron kind of talked about when we were discussing t-tests, he described t-test generally as like a signal to noise problem. Your signal is the observed data and you have some noise around that data. You want to figure out whether there are differences between groups when you're looking at t-tests. In the case of regression, we can also formulate this as or frame it as kind of a signal to noise problem. The signal is our estimated slope of negative 5.3, and the noise is basically the standard error associated with that slope. And in the face of the statistical noise that we have, we want to figure out if that slope is actually significant, if there is a true relationship between x and y, between weight and fuel economy. And so if we frame regression as this signal to noise problem that's very similar to a t-test, we can evaluate whether or not our slope is significant by turning to a t-test. And we can calculate basically a ratio between the signal and the noise by calculating a t-value. And the t-value in a simple single parameter linear regression is calculated simply by taking the slope and dividing it by the standard error. And that's going to give you this t-value. In the case of our regression example, the t-value is negative 9.559, and you can see that reported. It's kind of hard, the columns here are hard to interpret, but that's the t-value that's actually reported in your ordinary least squares summary. Okay, so once we've got a t-value, we've got this basically signal to noise measurement for our slope and our standard error. We next want to test if that slope is actually significant. And we want to essentially ask if the signal to noise ratio we're observing between our slope and standard error is more extreme than we would expect by chance given our null hypothesis. In the case of regression, or in the case of a simple t-test between two groups, our null hypothesis is that there's no difference between the group means. What's our null hypothesis when we're doing a regression? Well, our null hypothesis in a regression is that the slope is 0, that there's no relationship between our x and our y values. So if our slope point estimate, or our null hypothesis is that the point estimate is 0, then the t value is also going to be 0. And that's our null hypothesis. No relationship between x and y. So the question basically becomes, given that null, is the t value that we've calculated more extreme than we would expect by chance? And we can do this by just looking up our t value on a t distribution. Now, you may also remember from Aaron's lectures that when we do t-tests, when we look up t values on t distributions, we have to keep in mind the degrees of freedom in our analysis, the number of values that are free to vary in our analysis. So let's do that for our regression. Now, you might expect that in this analysis, we can see how many x and y values we have. We can just get the length of the miles per gallon array and the length of the weight array from empty cars. And we can see that we have 32 pairs of xy values in our data set. So does that actually mean that we have 32 variables that are free to vary, 32 degrees of freedom? Not exactly. It's actually a little bit more complicated than that. And when you're doing linear regression with a single predictor, you actually have n minus 2 degrees of freedom. So in this example, we actually have 30 degrees of freedom. And I've included this slide, which we can kind of walk through to figure out why that's the case. And I think I've described this accurately, but someone can feel free to correct me if I'm off here. Essentially, in regression, the degrees of freedom are always calculated as n, the number of data points in your model, minus k, where k is the number of parameters we're estimating. In this case, k is 2, because we're estimating a slope parameter and an intercept parameter. And the reason for this is basically if we know k parameters, in this case slope and intercept, only n minus k of the data points are actually free to vary. This is because we can always infer the values for k dependent variables as long as we know, we can always infer the values, is that right? For k dependent variable measurements, yes. As long as we know the values of our k parameters, our 2 parameters, slope and intercept, and the values that are taken on by the remaining, in this case, 30 data points, observations. So you don't need to worry about this too much, but if you're doing a simple linear regression and you're estimating 2 parameters, slope and intercept, y equals mx plus b, the degrees of freedom in your analysis is just going to be n minus 2. It gets a little bit more complicated when you introduce multivariate regression, but we'll probably talk about that. And similar patterns hold. It's just n minus k. Okay, so we're doing a t-test now. We're coming back to this t-test. We have our t value of negative 9.559, and we know that in our analysis we have 30 degrees of freedom. So we can first visualize a t-distribution on 30 degrees of freedom, where it's a little tough to see here, but on the x-axis we have our t values, and on the y-axis we have the probability of observing that t value. And you can probably already tell here that if our t value is negative 9.5, it's probably going to be way out on the fringes of this t distribution. But you can imagine that in our null hypothesis, the t value is 0, our slope is 0, and this is where our t value would be. But in our actual regression analysis, we calculated a t value of negative 9.5, which is way, way out on the fringes of our t distribution. And what this means is that the t value that we have observed in our regression is much more extreme than you would expect by chance alone, given 30 degrees of freedom. And this is essentially what's being reported here in the p-value column of your output table. The probability of observing a t-value this extreme, given the null hypothesis that there's no relationship between x and y, is 1.29 times 10 to the negative 10th. This is pretty highly significant. And again, just reiterating that our null is that beta slope is 0, and thus t is equal to 0. Our observed t value is much more extreme than expected by chance. And so what's clear here is that when we calculate p-values for simple linear regressions in R, all we're doing is doing t-tests. It's actually that simple. And in fact, the column here doesn't just say lowercase p. It's not reported as just a p-value. It's reported as the probability of observing a t-value as extreme as the one that we've observed, given the null hypothesis. And that's what's actually being reported in this table in R. Okay. Yeah.
It's like a single tailed, if it defaults to like double tailed.
I believe because of the absolute value symbol, it's going to be a two-tailed t-test, I think. I don't know. Somebody can correct me if I'm wrong here. We could test that, I guess. I mean, we could run that in R. But I assume it's a two-tailed t-test. Okay. So the same exact thing is done for your intercept value. I won't actually spend much time on that. Generally, we're more interested in what the slope parameter is because that's the main predictor that we're interested in. But you can see here that the same exact thing is done for this intercept estimate where we've got an estimate, standard error, divide the two to get your t-value, look up the t-value on a t-distribution with 30 degrees of freedom. You'll notice here that R just tells you that the p-value for that is less than 2 times 10 to the negative 16th. That's the lowest p-value that R will report in an output like this. If you see a p-value that low, it's probably pretty significant, so I wouldn't worry about the exact value too much. But that's what R is going to default to if it's any lower than 2 times 10 to the negative 16th. Okay. So there is a final part of that model output after we've done our t-tests for slope and intercept, which is this last little bit here. I'm actually for now going to skip this residual standard error, and I actually want to spend a little bit of time talking about what the R squared and the F statistics are. They're actually making pretty good time, so I probably would have had time. But anyway, we'll talk about R squared and F statistics for a second. So these are just more pieces of the model, more aspects of the model that you might be interested in extracting once you fit least squares. So the first thing, the multiple R squared, this is simply the squared Pearson's correlation coefficient. So you can take the correlation coefficient that you calculated with COR, or you can do it manually like we did before with our toy X and Y values, between weight and miles per gallon, square it, and that gives you just the multiple R squared value. So this is an informative metric because basically the multiple R squared value tells you what fraction of the variance in your dependent variable, the Y variable, is explained by the predictors in your model. So you can imagine that if you were just to plot a distribution of all of the Y values in the data set, you're going to see a spread. There's going to be a lot of variability in fuel economy between cars. And maybe you want to understand how much of that variability is actually explained by just the weight of the car alone. And what the multiple R squared is telling you is basically 75% of the variability or the variance in fuel economy can be explained by just looking at the car's weight. And so this is a pretty informative metric and is sometimes useful to extract once you fit a linear model. Now the adjusted R squared, again, I won't go into too much detail about, but the adjusted R squared is essentially just the multiple R squared after you adjust for the number of predictors in your model. So you can imagine that the R squared, the variance explained, is going to increase as you continually add more and more predictors in your model. I mean, you could predict fuel economy as a function of every possible measurement you can make about a car, about automotive metrics. And you would expect that the R squared is going to improve. But what the adjusted R squared tells you is in a sense, how much better those additional predictors are doing than including just one fewer predictor. And so it's kind of adjusting the variance explained by the fact that you're adding more and more predictors into your model. So the adjusted R squared is often useful if you're comparing nested models, which we'll probably get into a little bit later. But for the purposes of a simple linear regression, these two values are going to be pretty similar. You wouldn't expect them to be all that different. Okay. But the last thing here is this F statistic. And the F statistic comes from an F test. And an F test is also a hypothesis test that you can do to basically figure out how good your model fits your data. This is also often useful if you're comparing nested models. Nested model meaning that you take one model, add an additional predictor, ask if that additional predictor improves the fit of the model. You can add even more predictors after that. In a simple ordinary least squares regression, the F statistic can actually be calculated by just squaring your t-statistic. So this is just negative 9.559 squared. That's not all that informative. It's not very intuitive. So we're actually going to look at how you arrive at an F statistic like that and what the F test is actually doing in practice. But in some ways, the F statistic is also just kind of a measure of signal to noise, just like your t-test for slope or intercept term would be. Okay, so the F test is in essence an ANOVA, an analysis of variance. Now, for those that are familiar with analysis of variance, this might be pretty straightforward. For those that aren't, we'll actually walk through what's happening here. But essentially, you're comparing two models. Now, it might seem hard to compare two models when we're already defining a very, very simple model, which is just fuel economy as a function of weight. But what the ANOVA is doing is it's first defining a very simple model, M1, that is predicting miles per gallon as a function of 1. And what that syntax means when you're predicting some y value as a function of 1 in R is you're basically saying that the line of best fit in this model is just a straight horizontal line that extends out from the mean value of y. So no slope, and that line is centered at the mean value of your dependent variable. Basically, what's likely to be a pretty uninformative model. And you're comparing that model to M2, which is the true model that's predicting fuel economy as a function of weight. And then you're doing an analysis of variance comparing your second model to your first. And you'll notice that these two models are nested, so to speak. They're nested because this model is adding just one predictor to this model. They're essentially the same, only one variable has changed. And when you run an ANOVA comparing model 2 to model 1, this is the output that you get. And we won't really dive too much into the model output here, but it's reiterating that model 1, in this case, it's kind of switched them, but model 1 is your miles per gallon as a function of weight. Model 2 is this model that's predicting miles per gallon with no slope, a line that's centered at the mean. You report your F statistic here, which is the same as we saw in the original model output, 91.375. And you see actually that the p-value reported here is exactly the same as the t-test that you did for the slope in the original ordinary least squares model. And this is always going to be the case. If you have a single predictor and you're comparing to the simplest possible model, the p-value returned by an ANOVA is always going to be the same as the p-value returned by the t-test for slope. Because really the only thing that's changing between these two models is the slope. Okay, visually, what does this look like? Essentially, what we're doing when we're calculating this ANOVA between model 1 and model 2 is we're comparing two models. The first model is this one, where we're predicting miles per gallon as a function of 1. And if you remember, that just means that we're taking the mean miles per gallon value and we're plotting a straight line extending out from that mean. No slope, no relationship between x and y, and you see that the residuals in this model are pretty large, as you might expect. Our second model, we're doing a little bit better because we're trying to predict miles per gallon as a function of weight, and you can see that the residuals here, even just by eye, are quite a bit smaller. And essentially, this is what we're doing with the ANOVA. We're comparing this model to this model and asking if the second one fits better. And as you can imagine, it does, and that's why the p-value is so significant. Now, this same syntax is going to be used when we get into multivariate regression. You can imagine you could add lots of different predictors to these models and compare them against each other. And you're asking the same question. Overall, is one model better than the other? And in this case, the answer is yes. So at this point, I'm actually going to close. We've talked through pretty much everything that's to be reported in an ordinary least squares model. Just some closing notes here. Whatever you think about covariance, it's basically telling you yes or no, do two variables covary? That's about it. Correlation is an adjusted form of covariance that tells you if they covary, to what degree do they covary, positively or negatively. I'll reiterate that OLS is machine learning. The significance of a predictor in a linear model in a simple case like this is just a t-test. That's the only thing you're doing to tell whether a predictor in a model is significant. And regression, like a t-test, can be framed as a problem of signal to noise, where the signal is your slope and the noise is sort of your uncertainty surrounding that slope estimate. So with that, next time, if we have some time next time, we're going to dig into multivariate regression. So what happens when you introduce more than one predictor into your model, moving past simple OLS. We'll talk a little bit more about ANOVA for model comparison and selection when you have many predictors. And we might get into the difference between additive predictors and interactions between predictors. And then if we have some time, we'll get into generalized linear models and maybe do some modeling of discrete and binary data as well. And dig into that a little bit. But for now, that's ordinary least squares, and we'll save the rest for next time. So thanks for your attention, and if anybody has any more questions, feel free to ask.